Good morning, pre-calculus students. How is everybody doing today? Can you hear me?
Yes,
Good.
sir.
Wonderful. Now, today we're actually going to continue with some of the topics we've talked about. Remember, we discussed the rational zeros theorem and how that can help us do the complete factorization, and then we touched some on an interesting problem at the end of the lecture where we needed to do some numerical estimation, and we talked about Descartes and the bounds theorem, just basically to give you a little bit more insight into how you work with polynomials. And hopefully those last two items will be something that will enrich what you know. They're not always the most important things, but they can help you to make your work a little bit more efficient. So what I wanted to do for the first problem, before we start talking about rational functions and asymptotes, again, one of your favorite topics from college algebra, I want to just do an inequality. Remember, I assigned 3.7 as basically a review of inequalities, which we covered in the first chapter. What 3.7 does is bring back those ideas, and then it will allow you to use some of the new concepts that you have learned in chapter 3. So I want to show you an example and work through it just as kind of a warm up. So let me share my screen with you. And I want you to copy this, but this is just a warm up problem where I can kind of give you an idea of what I expect you to do in this section. Remember, this is mainly review, but the idea is that we want to be able to possibly use some ideas that we have learned in section 4 and 5 of chapter 3, and maybe even sections 1 and 2. I guess all of it. I don't know why I'm just particularly looking at one section. They're all important. So for instance, we might have you solve the inequality. So the idea here is the technique is the same, but maybe we can use some ideas that we've learned in our previous lecture. So we have x cubed plus x squared minus 50x plus 48 is greater than or equal to 0. Now, of course, as we've worked on these problems, it is clear, I think, to everyone that when you try to find zeros of polynomials, this is not an easy task. And in some cases, the best that we can do, at least in terms of finding a solution, is to get a good numeric approximation. And that's really the content of numerical analysis, which is a very big field in mathematics, especially with the advent of the computer. So what we would do with this is you'd say, okay, well, Professor Ron, I need to figure out the zeros and then do the BV technique. So because this is a cubic polynomial, we can look at this and say we could try to apply the rational zeros theorem, hoping that there was actually a rational zero that would get the ball rolling. Otherwise, we might be up a stump trying to find the actual zeros of this particular polynomial. So again, remember the constant term here is 48. That's what P divides, and the leading coefficient is 1. So we're going to be very pragmatic here. P will have to divide 48, and Q will have to divide 1 using our division symbols. So what I'm going to do is I'm going to write 48 as 6 times 8, and we're just going to look at some of the factors. 2 times 3, and then of course 2 times 2 times 2. So this gives us 2 to the 4th times 3. Now, when we look here, we see that we have some negative coefficients. So we can try some of the numbers here that we would get when we look at factors of P over Q. And of course, since Q is 1, ladies and gentlemen, our factors would just be, or our candidates would just be factors of 48. So we can just make some judicious choices here. So we have a 1, a 1, a negative 50, and a 48. Now, of course, you can look at this and add up the coefficients, and even though what's interesting about this, and I should have picked an easier, a harder problem, but I gave you this trick last time, and I said, no, don't be checking those numbers that you know don't work. And so lo and behold, okay, well, look here, negative 50, 48 plus 1 plus 1. That's 50 plus negative 50. Can anyone tell me what that equals? That's not a hard question. It wasn't a trick question. What's
0?
50? Absolutely, absolutely. Kaylin, you get 50 points. So Kaylin has said, Professor Ron, 1 works. 1 is a 0. So this is what I keep saying. Always look at some easy numbers and think, well, 1 works. And if I use my synthetic process, then I can develop a quadratic and I'm home free, because we all know how to solve quadratics. So we checked, we see 1 works. So let's put 1 here. See, the synthetic process is going to give us the reduced polynomial. So we know 1 works. And so we're going to bring the 1 down. 1 times 1 is 1. 1 plus 1 is 2. And then 2 times 1 is 2. 2 plus negative 50 is negative 48. Don't you like the 1s? It really does give us a nice break here. And then 1 times negative 48 is negative 48 plus 48 gives us the 0. So that was a clear choice of efficiency here. So now we know that we have x minus 1. If 1 is a 0, x minus 1 is a factor. Again, very basic, but extremely important. And then our reduced equation is x squared, just follow the coefficients, plus 2x minus 48. And now you're like, okay, well, Professor Ron, can't all equations factor easily? And of course, now we can just use a 6, a negative 6, and a positive 8, and that'll give us the negative 48, and then the 2 with the z and w. So we really hit the jackpot with this one. Of course, last time, remember, we got imaginary zeros and irrational zeros, really unfortunate looking numbers. So again, with this last part here, we see AC is equal to 1 times negative 48. So we just focus on the negative 48 and use 8 and negative 6 as our z and w. So that's what we used here. So this was quick. So when you work the problems, basically these are review. You may utilize some of the concepts that we have actually introduced in the previous sections of this chapter. And now, of course, we're going to utilize the fact that all of these zeros have multiplicity 1, and we can use end behavior and the multiplicities to get a really quick sign test. Sign tests are fine as long as you do them correctly. Let's face it, if the sign test is wrong, that messes up the graph and everything. It messes up the inequality. So we have to make sure that if we do some efficient tricks, that they actually apply. So now the BVs will be a 1, a 6, and a negative 8. Those are our BVs when we set this equal to 0. These are the numbers that make each of these factors 0. So now we can plot them and do our sign test. So we have a negative 8. And then we have, and I won't, I'm not doing this very, just in the order numerically. The scaling is not so good. Don't worry about that. Just make sure they're in numeric order. And so now you can think of a test point here as negative 10, and maybe like a -3, and then say a 4, and then a 10, even though we don't really need these. If you want to be specific on checking the factors here, you can always do that. But notice we have preserved this inequality. We've simply factored it. So this is preserved. So the end behavior, that is when we have negative infinity down here, we start below the x-axis, and all of these zeros are multiplicity 1, so we have to cross. So that can give us the sign test for free. So end behavior, cross, 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 and we're done. Now, usually, if you watch some of the Smart Pen videos, I usually test the sign just to make sure that everybody's on the same page. So for instance, if we had the -3 here, we put in the negative, we'd have negative, -3 here, we'd have negative, and a -3 here gives us positive. Two negatives make a positive. So you can always check, but if you want to use the multiplicities and the end behavior, go for it. And so this is negative, and this is positive. So this is what I was talking about before. If you want to use the multiplicities and the end behavior, you can get the crossing. And that gives you a very quick way to assess the actual sign of this expression. And so now we need greater than or equal to 0. So all the zeros work because they make it 0. So we can check all of these. And then, of course, we need positive too. So we get a check for this interval, and then we get a check for that interval. And you can put X's elsewhere, but I'm not going to. We'll just assume that we're going to be affirmative today. So now this will imply that X, now in your WebAssign, they'll most likely say interval notation. So in the box, you're going to include the -8. So you're going to use a bracket because you're going to write your mathematics correctly and not expect WebAssign to read your mind. Please don't ever do that. And then we include the 1, and then we leave this out. Then we move over to the 6 out to infinity, and we connect it with the union symbol. And again, I think you're getting much better at this. I'm already seeing an improvement in your work. Ladies and gentlemen, correctness in what we do is important. Everything we do, we don't always expect ourselves to be correct, but anything that comes across our plate, we expect to be perfect. If we get an app on our phone and it doesn't work, we get upset. And then it's like, well, maybe some of the code was entered incorrectly. Maybe it defragmented. The idea is that we have to remember that as we become STEM professionals, that is, you're training to become a STEM professional, you have to remember that accuracy is very important. And that's why, again, you take your time to work through the WebAssign. And so now we see a very nice application of the ideas we already know, and now focusing on the new techniques, finding zeros with the rational zeros theorem, using multiplicities just to make the sign test more efficient. So I like to take the opportunity to bring in what we've studied in addition to the topics that we've already known, for instance, back in the first and second week, and tie everything together and see how we can do a problem that before would not have been available to us. So this is what I mean by 3.7. It's basically terms and ideas that you already understand that's peppered with a few of the newer techniques. So again, it's not something you have to spend a great deal of time on. Just kind of look at it as a way to continue to apply some of the new techniques, and also to just review. Review is essential. And we know that pre-cal, college algebra, the calculus sequence, it's all built upon what comes before. So that's a good way to kind of put everything together. Now, so remember, and this is very important, when we start thinking about the rational functions, again, we're talking about things we already understand, but we want to be able to add a few ideas, maybe to bump up our understanding. So first, what I've done here, ladies and gentlemen, is I have summarized some ideas about rational functions. Now, I want you to jot these down, but everything I'm writing here, you're thinking, well, this is like the end behavior, Professor Ron. You've got these infinities and all, and so I will tell you this: it's kind of like Jose asked me about the Newton's method, and the thing is that the Newton's method is a calculus technique, which is a numeric method of second order, which is based on the tangent line. And because it's a second order technique, the convergence is quick, like Simpson's rule in approximate integration that you'll learn about in Calculus 1. So we often encounter topics in pre-calculus that say, well, use a graphing calculator or whatever. And my idea is that, you know, we don't necessarily have to use it. We can talk about what we can do to actually affect a numeric approximation, and then say, when we get to calculus, we'll be able to fill in all the details. So again, when we start talking about end behavior, we're thinking about x becoming infinite or negatively infinite, which we're going to talk about a little in a few minutes. But first, we're going to go into an area that's maybe different from what we've been talking about. We've actually discussed this, but this is a little bit different situation. So just remember, even though I say calculus every time we have a lecture, what I'm trying to focus upon is that all these techniques we're learning in this class and reviewing will be essential when you study calculus. So remember that this is the foundation for the calculus sequence. Without this proper foundation, calculus is basically impossible. And when I mean impossible, it's impossible to have the success that every student wants in the calculus sequence. It's better now that you decide to put in the time to do excellent work. And then you can move forward, and then you can choose whatever career you want, okay? The universities want you to transfer with a solid foundation. So now let's look at this. The WebAssign uses a lowercase r. I sometimes write it as uppercase r, like we do the remainder in the division algorithm, so I'll leave that up to you. But a rational function is just a ratio of two polynomials. And what we're going to do is use the p and the q like we did for the integers p and q in the rational zeros theorem, but now these will actually be polynomials. So what do we mean by vertical asymptote? Okay, so this is what I want you to put down here. So we're going to assume that r of x is a rational function. Now, I will say this many times. The vertical line x equals c is a vertical asymptote of r of x. Let me say that one more time. A vertical asymptote of a rational function is a line. So it must be written as a line equation, x equals c, okay? We often miss problems on WebAssign because we do not state things correctly, or we don't format things correctly. So an asymptote, a vertical asymptote, is a vertical line. So it must be x equal some number. Now, how do we know we have a vertical asymptote at this point in our careers? What that will mean is that the q evaluated at c is 0, but the p evaluated at c is not equal to 0. That's very important. If they were both 0, that's what you call a hole in a function. And it's not an asymptote. It's just a hole. And it doesn't create any infinite behavior in the function. Very, very different. And as we have time, I will talk about that. So why do you care about this? Well, the important thing is that the vertical asymptote helps us to get a reasonable graph of the function, because near the vertical asymptote, the values of R of X become infinite. So as X approaches C, and this is the notation I will use in your calculus class, we'll just say we've got the number C, and we've got these little triangles as like arrows to approach C. So we can approach from the left and we can approach from the right. Sometimes maybe we'll just approach from one side. It just depends what the domain of the function is. So what's going to happen, and this is what we're going to prove in calculus, but for now we will be comforted with the fact that we will assume the calculus is correct. What's going to happen as you approach C from either side, the function becomes infinite. That is, it's either plus or minus infinity from either side. So I've got this, and of course this could be an and or, and really I'll do that because we don't really know. In most cases, we'll approach from both sides. Now you're thinking, okay, here we go again. This is like in behavior. We have to determine what sign do we affix to the infinity. Well, the sign here will be taken care of with the sign test that we've been doing with inequalities. So there won't be anything new there. We'll just do a little sign test and figure out, do we get plus infinity or minus infinity? If the sign is positive, you know, as we approach the left, we look on the number line, then we do the plus positive infinity and vice versa. So there's nothing new here to affix the sign. It's just the sign test, the BB technique that we've been doing. So I wrote this in red. We must determine the sign of infinity. Now, what I've written here in a box is that these are infinite limits. The limits are infinity or minus infinity. And so you're thinking, is that really a limit, Professor Ron? Because you know, you told us infinity is not a number. So in the proper context of calculus, infinity is not a limit, but we get kind of shaky with our terminology and basically say, okay, we're saying that the function either becomes arbitrarily large or infinitesimally small. And that's good to know. And so when we graph our functions, we use that idea. So again, this type of analysis here will allow us to get a reasonable graph without having to plot 500 points like a fancy calculator would. Now, of course, the calculator can plot the points in a nanosecond, and how nice that is. But you get accustomed to that, and then you lose your powers of computation. So we'll talk about that and graph some. Okay, so the vertical asymptotes are basically, it's like finding the domain of a function. You look in the denominator of the rational function and you say, okay, where can it be zero? And are those zeros just in the denominator? Are they repeated in the numerator? So we may have to make sure that whatever zero we have downstairs is not a zero upstairs. That's important. If you ignore that, then that can cause grief. Now, the next part that we need to consider will be the horizontal asymptote. Now, some of you have already started working on these problems because you've asked me, Professor Ron, how do we compute the slant asymptote? And I thought, well, very good, you have worked ahead. Well, here's the thing. Let R of X be a rational function. Okay, again, the horizontal line, y equals c, is a horizontal asymptote of R of X, if and only if. Now, this is what's going on here. As X tends to infinity or negative infinity, that is and or, the limit is c. So instead of the function becoming infinite or negatively infinite, it approaches a finite number. So again, we get another asymptotic approach. That is, the graph approaches a line, but in a horizontal fashion. and it's a finite number, like maybe the graph approaches the horizontal line 2. So this is end behavior. But it's not the end behavior, ladies and gentlemen, that we see with the polynomial, because with the polynomial, the function blows up. But here, it settles down. So when we have this fraction here, when we have the fraction, this introduces some new calculus for us. So now you're thinking, oh, okay, so here we've got x approaching a real number, and the function becomes positively or negatively infinite. That's an infinite limit. Here, we have x approaching infinity or negative infinity, and the function approaches a finite number. This is what we call limits at infinity. The limit occurs at infinity here, and here the limit is infinity. So we're thinking, you know, wow, we've got two extremes here. Now, of course, the vertical asymptotes are easy. You find zeros with no problem. That's the easy part. Again, that's like doing a domain computation. You're already well versed at doing this. Now, with the rational functions and the horizontal asymptotes, we have some rules. And these are basically rules that you'll be able to prove in calculus once you study limits with a little bit more detail than what we're doing in this class. So what we do is this. We look at the degree of P and the degree of Q. Remember, R of X equals P of X over Q of X. And with that, we have these rules. So we look at the degree of P and we look at the degree of Q, just as polynomials, the largest power of X. And then we say, if the degree of P is strictly less than the degree of Q, our work is done. The horizontal asymptote is y equals 0. No work to be done. Basically, what that's saying is that as x becomes infinite, the numerator gets small relative to the denominator. That is, the denominator takes over. It takes over because the power of x in the dominant term is larger. And so as x becomes more infinite, then what's happening is that relative to the numerator, the denominator gets large. And so the fraction converges to 0. And so the value of the function approaches 0. So when you've got a case like this, your horizontal asymptote is automatically determined. That's the first case of the horizontal asymptote. The second case just takes a little bit more work, but I've already talked about it because I've talked to you about ratio of leading coefficients. I've already talked about this 3 or 4 times in the previous work. So you're thinking, Professor Ron, you sound like a broken record. Well, here's the thing. When the degrees of P and Q are the same, that is, we think of P as being a polynomial of degree n and Q as being a polynomial of degree m, when these are actually equal, we take the ratio of leading coefficients. And that's the horizontal asymptote. Again, we can prove both of these using the calculus. But for right now, the intuition is, oh, the dominant terms have the same power. They have the same power. So they kind of absorb each other. And the only thing that's left are the coefficients. All the other terms, they just dwindle away because relative to the largest powers of x, they really don't have much impact. So again, we think when the dominant terms are the same in the polynomials, they absorb, and what we're left with are the leading coefficients. So at least what you can think of is that when you get to calculus, there will be some things that are already very intuitively obvious to you. And the calculus will just provide the arithmetic to verify that. And it will not be that difficult. You're going to find that a lot of these proofs are very straightforward. Now, the only other category that we're going to talk about will be number 3. So 1 and 2 give what we call the horizontal asymptote, the case where the degree of P is 1 more than the degree of Q. Say the degree of P is 2 and the degree of Q is 1. P has to have 1 degree, the degree 1 more than the degree of Q, just like I said. So if we have this equation here, we don't get horizontal asymptote. So I say no HA. We get what we call a slant asymptote, and it's going to be a line we get from the division algorithm. When we divide, it's the quotient. The quotient. And you're thinking, oh, if the degrees only differ by 1, the quotient's going to be first degree, and that's going to be a line. So when you have to find the slant asymptote for this category, you can either try the synthetic division. If it applies, you have an x minus c, or you do the long division, the division algorithm, and the y is just the quotient, the big Q of x that you have in the division algorithm. Because students always say, how do I get that slant asymptote? How do I do that, Professor Ron? You just divide and it's the quotient. That's it. So the thing is, this is the only new part. Everything else, ladies and gentlemen, will be old and will be the techniques that we've done before. Sign test, intercepts, you name it. So now let's apply some of this. Now, I do want you to know these concepts. They're not difficult, but I want you to know the basic rules for the horizontal asymptotes. Now, let's just look at a real easy one. Sometimes the most simple example is illuminating to the sense that you're like, wow, Professor Ron, even though this is easy, it's going to help me to illuminate the ideas you just talked about. So we're going to say R of x is 1 divided by x plus 4. And so you're going to think, WebAssign might say, well, why don't you figure this thing out, figure out a graph and do the sketch with transformations. But I'm just going to go ahead and exploit what I've just talked about. So here's what I want. I want asymptotes. That's a strange word, asymptote. Asymptotes, I want intercepts, if they exist, and I want a sketch. So this is like the reasonable graph that we have when we work with polynomials. So now you can just say, okay, well, this is so easy. The P of x is the polynomial 1, and the Q of x is the polynomial x plus 4. So P is 1, that polynomial, and Q of x is x plus 4. So first, let's go ahead and look for the VA, the vertical asymptotes. Well, -4 is a 0 of Q of x. You can just, boom, that doesn't take a lot of effort there. -4, set that to 0, you get x is -4. But that's not a 0 of P. P doesn't even have any zeros. So we'll say x equals -4. That satisfies the definition. Done. Nothing more to do. Horizontal asymptote. Well, again, if you like, degree of P equals 0. It's a constant polynomial, so by definition, it has degree 0. And we have the degree of Q. The degree of Q is 1, isn't it? The largest power of x. 0 less than 1. So this implies the horizontal asymptote is y equals 0. That's the first rule that we had right here. This one right here. So the thing is that they don't work sometimes, they work all the time. So this gives us our asymptotes. We got those for free. And now let's look for x-intercepts, and then we'll do a sign test. Okay, how do we get x-intercepts of a rational function? That would be where the numerator is 0, but 1 is never 0. So we say 1 does not equal 0. So there are none. The graph does not cross the x-axis. Now, ladies and gentlemen, these computations are simple. They are simple. Do not confound this by failing to accept the definitions of the asymptotes. This is very simple. This is actually easier than doing polynomials, but since you've got the asymptotes, we'll have to get practice with sketching them. That'll be the hard part. Now, the y-intercept. That means we just look at r of 0. What's r of 0? Well, if we replace x with 0, we just get 1/4. Okay, so that will be the point on the y-axis where the graph crosses, and then of course there are none on the x-axis. Now, if you want to do a little sign test, there's only one BV, and it's negative, negative 4. So you can think, you know, we've got a negative 10 and a 0. But of course, if we put in negative 10 here, we get negative. So we're like below and then above. So we have negative and plus. I like using the multiplicity type exercise now because, you know, that has multiplicity 1. So it's got to cross. But it's not really going to cross in the sense here. It's not multiplicity because the graph is not going to cross the vertical asymptote. What I'm saying here basically is that we have a sign change. And this is not like a polynomial because you can never cross a vertical asymptote. But if you want to think about this as a sign change, okay? So again, remember, we can't cross a vertical asymptote. We can, however, cross a horizontal asymptote, and I'll say more about that. So you don't think that we're actually crossing here. I'm going to remove that. And I'll just say negative and positive. So here we're below and here we're above. That way you don't think we're actually crossing there. So now we can get our inexpensive sketch. And we'll stretch out the axes and the tick marks in order to make the graph look reasonable. You know, when we're sketching a graph, we are in control, so we can pick a scale that makes our graph look really nice. So now notice we have x equal negative 4. So let's see, we've got the y-intercept of 1/4. So we'll spread this out a little bit. So we'll say 1, 2, 3, 4. So we'll sketch in our negative, x equal negative 4. So here's our x equal negative 4. And then of course, y equals 0 is the x-axis. And then we have, we'll spread out this a little bit. Let's say we've got 1, negative 1, spread that out a little bit, you know, be a little bit more generous on the y-axis. And so we've got a 1/4, say about right there. I'll do that in red. So there's our y-intercept. And of course, WebAssign always likes you to state when you compute the y-intercept, they like you to write the ordered pair. That's the formatting they like, and that's fine, and you do that, and you do that very well. So now notice we have above here, so we have the plus infinity here, so we approach like this. Let me get a good drawing here. We pick up the y-intercept, and then we approach the x-axis. So we get real close to the x-axis. Now on this side, we don't have any driveways here, so we have to approach the x-axis, but then we have to approach the vertical asymptote in a negative infinity direction. So now notice we do the sign test for the -4, x equal -4, we're below the x-axis, so we have to approach negative infinity. That gives us the negative infinity here. And then, of course, to the right, and if you like, you can just put your little arrows here as you approach from either side. And then from the right, we're plus, so we do plus infinity. And notice here that the only thing that we have to do is hug the asymptote as x becomes arbitrarily large, the horizontal, hug the asymptote as x gets negatively infinite. And then as we approach, in this case, our c is -4, as we approach the -4 from either side, we use the sign test to figure out, do we have negative infinity, positive infinity, or whatever the case may be. So here's a very, very simple function. If you already knew what 1 over x looked like, then you'd be fine. But I wanted to address this from a completely rational function standpoint. So anytime that we want to try to graph a rational function, and we want to get the most output for the minimal input, we will do this. We'll do the asymptotes, we'll do the intercepts, and sometimes you're thinking, maybe I can cheat and not do the sign test. But the sign test is usually good to have just as a way to check things. In some cases, it may seem like overkill because you don't really need to check anything. And again, the function may be sufficiently complicated that we would maybe want to check to see if the graph actually crossed the horizontal asymptote. Just remember, the graph will never cross the vertical asymptote. We can think of the vertical asymptote as an infinite object, like a black hole. The infinite gravity, so to speak. So the graph will never cross the vertical asymptote, but it can possibly cross the horizontal, but it doesn't in this case. So now you're thinking, oh, Professor Ron, we're so good at this. Look at this, the domain of R. We did the domain when we did the vertical asymptote. The domain of R would just be all reals except -4. We might as well go ahead and write this down since we know it. And then if you think about this, the only thing that doesn't get hit is the horizontal asymptote just by looking at that. So we say the range of R, we can never be 0 because the numerator can never be 0. So we have negative infinity to 0, union 0 to infinity. Okay, so the idea here is very simple. The only new parts here, everything else is old, this right here, the asymptotes. And you actually already know how to do this because you did this in college algebra. Okay, so let's try another one. This is important because when you get to curve sketching in calculus, we will add the calculus part to this stuff that you already know. So you can still get what we call a fairly decent graph, not much detail when it comes to the peaks and the valleys and the actual concavity, but we can get a reasonable graph just by using the fact that we want to draw something that's not jagged. The differentiability of these curves you will prove in calculus. That's why we draw them smoothly. They're not jagged, okay? You're thinking, well, why do we know to do that, Professor Ron? Nobody told us about that. Well, the calculus provides the smooth curve, and we can't do that right now. But for now, we will make these curves as smooth as we can, okay? Let's try another one. As Dr. Lima Philo, my topology professor at A&M, he says smooth curves. He always laughed at us because he thought that, you know, our lives were too easy. He says, you all have computers. And I learned in the dark ages. Well, when I went to undergraduate at Carolina, that was pretty much the dark ages. So I think I was the only one in the class who understood what he was saying. So now let's look at another one. Here's one that's going to have a slant asymptote. So we're going to have T of X. You know, Webber-Sign gets really clever. They just call the rational functions by any letter. So you be flexible too. And whatever variable the function uses in the problem, that's what you use in your response. Ladies and gentlemen, if it uses if the independent variable is x, you use x. You don't change it to z. Okay. So many of you will do that because you're just not being careful. You think about that. Say you work for some big engineering firm and you change all the z variables to z, or z variables to x, and then the program derails and the production process stops and the company loses $50,000 for that mistake. What I'm saying is that it does matter how you input your responses. They must be consistent with the problem. And that's hard to do. That is hard to do. You have to double, triple, quadruple check. So we've got x squared minus 2x minus 24. Now just remember, when you have these problems, the zeros will be reasonable. We're not trying to make you, work for everything. We want to be able to give you some good techniques with some reasonable calculations. Now, first, let's just go ahead and say this is P of X over Q of X. And notice that's an X minus C. The degree, and I'm just going to go ahead and make some comments here. The degree of P is 2. We'll go ahead and take care of this since it's an obvious situation here. Degree of Q, the denominator is 1. So we say 2 equals 1 plus 1, or 1 plus the degree of Q. That's the third case, and that means slant. So this implies slant. Sometimes they call it oblique, slant asymptote. It just means it's not a horizontal asymptote, it's slant. Slant, not horizontal. Sometimes you will see the word oblique. So don't be surprised if you see it written that way. It's the same, it's synonymous. So, okay, so let's just go ahead and figure out this. We just need the quotient. So this is synthetic, so I'm going to be lazy and use synthetic. So we have our 10. Remember, there's the minus C, so the C goes right there. So we have 1, negative 2, negative 24. We just need the quotient. So now it's interesting here. We bring the 1 down. 1 times 10 is 10. 10 plus negative 2 is a positive 8. And then we have an 80. 8 times 10 is 80. Subtract 20, we get 60. So that'll be what, a 56? I think I actually did work this out, yeah. But I don't care about that. That's the remainder. And we don't, of course, it's not going to give us a 0 remainder. Otherwise, this wouldn't be a slant asymptote. So now right here, there's the quotient right there. So y equals the quotient, which is x plus 8. That's the slant asymptote right there. Now, of course, if we couldn't have used the synthetic here, we would have done the polynomial long division, which is fine. It just happens to be the case that that has the x minus c form for the q, so we can go ahead and use the synthetic process. So again, remember, the slant asymptote, when this actually occurs, this situation occurs, is the quotient. This is a line. Remember, that's a line, a first degree equation in the variable. I'm not going to say it's always x. Maybe it's x of t, and all these x's are replaced with t. It could be that way. So now we've got the slant, so we'll just say slant asymptote. So that took a little bit more work. Maybe you'll have a WebAssign problem that just says, what's the slant asymptote? That would be easy, just one answer. And now vertical asymptote. First, let's go ahead and factor this. We have t of x equals, and notice here we can use a -6 and a 4 because we've got the AC method with some easy factors. So x minus 6 times x plus 4. And notice the -6 plus the 4 gives us the -2. And then the -6 times the 4 gives us the -24. So those are good candidates for Z and W. And then we have X minus 10. So what I was basically trying to show you here is that the 0 of 10 here is not a 0 of the numerator. So that gives us the vertical asymptote. So we have VA X equals 10. All right. So like I say, the new parts are the asymptotes. That is the vertical asymptotes. We don't have, we don't have too many special cases with the verticals. The function just becomes infinite in the neighborhood of the vertical asymptote. And those are pretty simple to figure out. The slant and the horizontal, again, we just have to follow the 3 rules that we have. Now, for x-intercept, we just look at the zeros of the numerator and we bother to factor it. So we get a 6 and a -4. And then for the y-intercept, basically we can do t of 0. We don't want to do it here. We can, but it's easier just to look at it there. This is t of 0. So 0, 0, -24 over -10. But of course, the only common factor there is a 2 and the negatives absorb. So that's 12 over 5, which is really, 2 2/5 if you want to think about, writing that, thinking about where you're going to plot it. So the idea here is now we have a slant asymptote. So instead of the curve approaching a horizontal line, it's going to approach a slanted line. And this slanted line has a slope of 1. It has a y-intercept of 8. Now, in order to make sure that the picture looks right, we want to do the sign test. So we've got our BVs. So just write those down, BVs. We have a 10 here. Again, we don't cross. Even if I draw it crossing, I'll try not to. I'm not trying to say that we cross the asymptotes. We get a 6 and a -4. So we can do a little sign test. And notice these are all degree 1. Okay, so the sign will change. So we have what? -4. We have +6 and a +10. So if you wanted to check like say a -6 here, we could say like a 0 here, and then an 8 here, and then maybe like a 15 here as checkpoints if you wanted to check those. So now what we can see, and we're going to have a sign change at all of these zeros or places where the function's undefined, because all of these multiplicities are 1. So that's just a little trick that I'm adding now. I used not to do this. I'd have the students check everything, but I think we're getting to the point now where this is clear. So let's just check the -6 here. So negative, so that's a negative. And then negative here, -6 will be negative. And then negative here, that'll still be negative. So 3 negatives is negative. So we're below. Now, of course, we got the -4 here, so we're below, and then we have to cross. Now we have to come over here, and then the 6, we're going to have to cross, and then we're below. But I'm not going to draw it at 10. I'm just going to do like that and not write the cross, because that's a vertical asymptote. But we have negative, positive, negative, positive. So you can go ahead and check all the signs, but since the multiplicities of these factors are all odd, namely 1, we know it's going to change. So that's just a little trick to move the problem forward a little bit quicker. Now we've got the infinities right. So now if you want, you can do your little arrows here. As we approach 10 from the left, we're at negative infinity. And as we approach 10 from the right, we're at positive infinity. So that gives us that. So now what we want to do is draw a picture. Let's put in the asymptotes first and give a scale that will make our picture look good. You know, sometimes the scale's not big enough and then the picture looks terrible. So we'll try to spread things out. We've got a 10 and we've got a 6 and a -4. So we'll give more space to the positive part. So let's do that so we have more room. We're drawing into axes. Okay. So there's our x-axis and our y-axis. And so now let's see here. We'll go ahead and set this up where we've got, let's see, we've got an x-intercept. So we'll do these like in fives. Let's say here, we've got like a 5, and then a 10. So we'll break this up a little bit so we can do the, so like a 5 here, so like that. So that's a 5, and then we'll do like a 10, and then like a 15. So now let's go ahead and get some of these intercepts. We've got, oh, and let's do over here a -5, about the same. So we've got a -4 about right here. That's an x-intercept right there. And then we have a 6 about right here. We got that. And then we have a y-intercept of 2 2/5. So say we're about right. So 1, about right there, maybe. Right there. And let's go ahead and sketch in our asymptotes. So here's how we do these pictures, ladies and gentlemen. We plot the intercepts and then we plot the asymptotes and then we use our sign test to fill in the curve. I rarely do a rating. You know, I like to speak to people in person, but I told Amazon I like my IPEVO document cam all the way from Japan. So now here's our x equal -10. And let me get a little, let me move Professor Ron over a little bit. Yeah, get that focus just right. And so now we've got this slant asymptote, y equal x plus 8. So the 8, so we've got like 6, 7, 8. There's the y-intercept right there. And so, of course, the x-intercept would be -8. So 6, 7, 8. So we'll connect these two lines, or 2 points. So this is y equal x plus 8. So now we have to hug this line, but notice we've got to hug this line, we got to pick up these points and then hug down here because on the left, to the left of -10, we're at -infinity. So we have to hug this line and pick up these points. So this is the non-calculus graph. And it's not half bad, even though there's a lot of stuff we're leaving out. We don't know where the peak is here, but at least what we're able to do is hug the slant asymptote and then pick up these points. And then our sign test says we have to be -infinity as we approach from the left of 10. And then here, this is the easy part. There are no driveways here. We have to be at +infinity here and then approach this so we get a little valley, something like this. Okay. So the calculus would allow us to find the maximum point here, the local max, and also the local minimum here. And then, of course, like I say, when you draw it, I could have done the scale a little bit smaller maybe and get a little bit more of this graph. But now what you're seeing, ladies and gentlemen, is that we have a really odd looking graph that's clearly not one-to-one. I mean, it's not one-to-one, and it would, we could chop it up if we knew where the maximum was here and the minimum was there to get a one-to-one function. So without the calculus, this is about the best we can do. Now, let me just say this one more time. The key to doing these rational graphs with no calculus is to first draw them as smoothly as you can, use your intercepts as guides, use the asymptotes as guides, and then with the sign test, you know basically what's going on. So for instance, when we look here, we're below the axis to -4, and then between 4 and 6, we're above positive. And then from 6 to 10, below, and then from 10 on, above. So this little sign configuration here is actually a really nice tool. You could have looked at this and said, well, that's what I have to draw. I don't even if I didn't do this, I would have to draw this. And then, you know, you're always thinking to yourself, do we cross? Usually you don't have to check crossing the asymptotes, but there'll be instances when you might think, I don't know, I don't really know how to draw this picture unless I check this. With the sign test, the way it's set up here, we're pretty much in the clear. You're thinking, will this ever cross here? It won't. And again, if you wanted to do that, you could just set this equal to x plus 8 and show that there is no solution. But again, we'll talk about that later. The main thing is to be sure that you use the intercepts and the asymptotes in conjunction with the sign test to get a reasonable graph. And notice we plotted what? 3 points, and we plotted 2 asymptotes. That's it. You know, you can use a fancy calculator and find and learn absolutely nothing, or you can do it this way, and you can teach your friends who struggle with this how to do it. Okay, so the slant asymptote is a little bit more complicated in that we have to work a little bit harder to graph it, but the sign test is the same as we've been doing with the inequalities. Okay, so let's try another one. Now, when I say let's try another one, the only way to get any good at this is to keep doing several. And again, use what you remember in, what is it, the class you took, college algebra? Use what you remember in college algebra and add to it maybe some of the new things we've talked about today. So here, let's look at this one. Now, in some of the WebAssign problems, ladies and gentlemen, they may just say, what are the asymptotes? Like I said before, you don't have to do a sketch. In some cases, they might say, what are the intercepts? No sketch. I would say this, when you work through all the problems, go back and sketch the ones that didn't ask for a sketch. Okay, so here we have R of X equals, this is a neat one. This is like the ones we did back with the inverse functions. So we have 2x plus 8 divided by negative 8x plus 4. Now, first of all, I just want to do a little bit of algebra here. So in the first case, I'm gonna factor the 2. So I'm going to get an x plus 4. And then downstairs, I'm going to factor the negative 8. And so that'll give us an x. And of course, if we divide the 4 by negative 8, we get a negative 1/2. So what I wanted to do in this particular case is to highlight the zeros, and then we can go ahead and reduce this if you want. The 2 and the 8 will absorb. So we just get x plus 4 and we have a negative 4x minus 1/2. That's just some additional algebra there. It's not basically required, but it highlights some zeros, just like we were doing an algebra problem. Now, what I want to notice here, this is unlike the last one, because when we look at the last one here, we had disparity in the, or differences in the actual degrees. We had a 2 and a 1. Here we see, and we can write this way, P of X over Q of X. Now, you might be thinking, well, Professor Ron, you've done all this nice algebra here. You know, you can call this P of X, you can call this Q of X. Here we've reduced things, but we haven't changed anything. The actual statement of the polynomial changes if we move from here to here, but they have the same attributes. This is what I was talking about with the student in the conference hours. You can factor and multiply polynomials and not change the zeros. And then, of course, as long as you're multiplying by non-zero constants and you don't change the degree either. But now this was just to highlight the zeros. So that's just a little extra practice for you. Now we see that the degree of P is 1 and the degree of Q is 1. They are equal. So we say degree P equals degree Q. Now I know I'm kind of beating this to death, but this is rule 2. So now we take the ratio of leading coefficients, that is 2 to -8 or 1 to -4. So this gives us y equal -1/4. So this is the horizontal asymptote. And I'll say ratio of leading coefficients. Now, you have to admit that some of this is a little bit dry, but when you get to calculus, you're not going to leave any of this at the door. You're going to use all of this, and maybe basically you're going to utilize the calculus to get some extreme points, maxima and minima, and then also to develop some ideas about concavity. But the thing is, none of this will ever get old. So don't think that you will dispose of any of this when you get to the calculus. Now notice here, the vertical asymptote is clearly defined as x equal 1/2 because that's a 0 in the denominator. That's why I factored this, but clearly 1/2 is not a 0 of the numerator. That's why I factored this so you can easily see the zeros. So we have the HA, I did that first, and then the BA would just be a 0 of Q that's not a 0 of P, and so we've got x equals 1/2. And of course, you can have more than one vertical asymptote. The thing is, if you can do this, we can have 2 or 3 if you wanted. We can make up our own factored rational expressions and have a much easier time than having to decompose all of this. And so now the x-intercept will just be the 0 in the numerator, which is -4. And the y-intercept, this will just be r of 0. Well, if we'll go back to the original, r of 0, these are both 0, so we get 8/4, which is 2. So the idea here is that the analysis, very similar to the last problem, but we didn't have to work as hard because we did not have to determine a slant asymptote. We just did the ratio of the leading coefficients because the degree of P and the degree of Q are equal. But now you're looking at this and saying, Professor Ron, I bet this is 1-to-1. We could prove this is 1-to-1. This is what you did when we studied this. And you're exactly right. So now we can see that the domain, we can go ahead and write this down. The domain does not include 1/2. And then, of course, when we think about this horizontal asymptote, the range could never include -1/4 because you would never hit that because of the 8 and the 4. So if you want, just say domain will be all real numbers except 1/2. And the range would include all real numbers except -1/4. All right. So just basic analysis here that will be very helpful in calculus. And now we can just go ahead and do our little sign test. Now, of course, if you're running out of time, you can just go ahead and slap on the intercepts and the vertical asymptotes and do a quick sketch, or maybe you're running out of time and you can look at the graphs on WebAssign. Well, that one doesn't make sense. Those three don't make sense. That must be it. Check, and you get it right. I mean, clearly that can happen, but we just want to cover all the bases here. So now let's just see here. We've got an x-intercept of -4, and then we've got a BA. So here are our BBs. So we'll say BBs 1/2 -4. Where's the function 0? Where is it undefined? 1/2. And so we could do like a -1, a -10, and a 3. Now the thing is, when we think about this, we can choose any one of these. Here we've got a built-in negative, and these are all first degree, so we know it's going to vary. So let's first figure out this one. So if we put in -10, we have a negative, and then the negative is there built in, so put the negative in, and then a -10 there is negative. So 3 negatives is negative. So this is below. Now, of course, we're going to cross. So we're going to say below, and then we're going to cross. And then as we get to the 1/2, we're not going to cross through. We're going to do something like this. So the sign's going to change. So I'll just do a little break there because we don't cross the actual vertical asymptote. So we have plus and then a minus. So that gives us our sign. So we can think of, if we're on this side of the 1/2, we're going to infinity, positive infinity, this side, negative infinity. So now let's get a quick sketch, put in our asymptotes and our intercepts. So we can spread this out a little bit. So we've got a -1/4. So let's spread this out a little bit. What's our y-intercept? 2. So we'll do like a 1, so we can see our horizontal asymptote. We'll spread it out about like this. So you can be a little bit more flexible with these. So here our -1/4. There's our horizontal asymptote. So we'll say, we'll just say y equal -1/4. And then we have a x-intercept, and let me spread this out a little bit. So we'll say like 1, 2, 3, or make these a little bit smaller. So here's our -4 here. And then we have the y-intercept of 2. So here's our -1, 1, 2. And then we have the, let's see, I'm spreading this out a little bit. So I put the 1 about right there. So we have x equal 1/2. So right in the middle there. Just to give a little space so we can actually see it, x equals 1/2. Now, spread this out just a little bit. So now notice we're below the x-axis here, but we have to hug this line. So we're hugging this line, and then we cross, and then pick up this point and then go up here based upon this sign convention, because here below at 4 we cross and then we stay above the x-axis. So we'll get something like this. So nice and smooth. Okay. So this part basically just runs this way, hugging the horizontal asymptote y equal -1/4, picking up the x-intercept and the y-intercept, and then we hug the vertical asymptote x equal 1/2 in the positive infinite direction here as we approach from the left. So above the x-axis, positive infinity. And then to the left, we're done. We have to be negative, down here, negative infinity, and then we have to hug this. And of course, we don't cross because there are no driveways or intercepts here. So this part, this was the easy part here. So again, just draw it as smoothly as you can. Now here's another thing that again, this is no proof of the one-to-one. We would prove the one-to-one algebraically, but when we draw it, it should look one-to-one, and it is. We do have a one-to-one function, and this graph at least displays that, even though I'm not going to get any art awards for my rendition. But again, we have this piece, this branch, and this branch. Now, again, what's the calculus going to show us? The calculus is going to say that we definitely always have an increasing function. We drew it increasing because it seemed that would be the only way we could draw it, but that's not a proof of it. This doesn't tell us anything about the function. We figure that out analytically. Again, if you're under the mindset that the graph tells you about the function, then that is a complete falsehood. And if you have learned that way, I will never teach that way. Students will say, well, if I knew what the graph was, I could answer this question. Well, no. The graph comes because you understand the function. It is not the reverse. And that's what the fancy calculators have done to your understanding of mathematics. They've basically ruined it. So don't rely on them. Rely upon your ability to do analytical work with the mathematics. And so now what we can see is, aside from the calculus, we have a decent graph. And what's the calculus going to do for us? It's going to show us about the concavity here. It's all going to show us that this increasing that we've drawn is correct. It's going to show us about the concavity here. And it will also prove that this function has no relative extrema, because right now it doesn't appear that it has any, but we don't know that. We'd have to use the calculus. So what we do in pre-cal is we do everything we can. We can get a lot of good information from this procedure. And then when we add the calculus, we will continue to do this and add the calculus on top. So that's why when students think about sketching curves, they're like, boy, we can go to town with this. We can, we can spend a lot of time sketching curves. Or I could be easier on you. I could just say, prove that R of X increases on its domain. And that would only require you to compute the derivative and not sketch the graph. So you can always minimize the amount of work. When we do this, we're kind of pulling out all the stops. We're always going to look at the asymptotes, the intercepts, and some type of sign test to affect a reasonable graph. So there we go. Now I want to look at one more. And like I say, when you do these problems, answer the questions. Do whatever calculations you need to do to feel comfortable. Don't worry. No two students do these problems the same, but the result should be equivalent. So let's look at this. So now we've got R of X equals 3x squared plus 6 divided by x squared minus 2x minus 3. So go ahead and look at that. There's another example here that I want to eventually cover with the inequalities. So when we look at this particular problem, the first thing you're going to notice is that the degrees are the same. We'll say more about that. But first, let's just go ahead and say, all right, well, we can factor. So we have a 3 times an x squared plus a 2. So, you know, complete factorization. Of course, if we kept going, we'd have imaginary zeros here. And so we're not worried about that. But if you had to do the complete factorization of the p, you could do that, square root of 2 times I, and negative square root of 2 times I. That I've taught you how to do. And here, of course, that's just a simple factorization. We can use a -3 and a 1. That's an easy Professor Ron AC lemma. So we would maybe take the z equal to 1 and the w equal to -3. When we add them, we get -2, and the product gives us -3. So that works. So we can think of, again here, this equals p of x over q of x. And the degree of p is clearly 2. The degree of q is clearly 2. They are equal. I guess the most fun problems are when the degrees are equal, or when we get a slant asymptote. And the slant asymptote is just division, unless it's so simple. What if the denominator is just x? That's the easiest one in the world. Sometimes you're given those, and those are kind of fun to do. So we've got the degrees equal. So we do the ratio of leading coefficients. We can do it here, or we can just look at it here. So this means y equals 3 over 1 or 3. Ratio of leading coefficients. So here's our HA. I guess it makes sense to look at the HA because that can require maybe the most work. I mean, factoring you're very good at doing, and so which one you decide to do first or whatever, I'll just leave that up to you. Now for the vertical asymptote, we just look for the zeros. We're basically trying to compute the domain of R of x, and we have a 0 of 3 and a 0 of -1, and they're clearly not zeros of q, or excuse me, of p. So the zeros of q are 3 and -1, which are not zeros of p. So we have x equals 3 as a vertical asymptote, and x equals -1. You can write down your own rational functions, ladies and gentlemen, and give them any qualities you like. You can give them whatever x-intercepts you want, y-intercepts, vertical asymptotes, and make up your own functions. There's certainly not anything sacred about what we're doing here. When you get bored, just try that, or just look for some additional problems in your ebook, or go to some of the practice tests and work through some of those. So now we've gotten the asymptotes, and now the x-intercept, or x-intercepts. For instance, now like we were talking about before, we know that the only zeros here are imaginary. That is, we don't get any real zeros here from a complete factorization. So here we'll say none that are real. So none, I'll just say no real solutions. I mean, when we talk about x-intercept in this class, we're really talking about real x-intercepts, and there are none. So we'll just say there are no real solutions. I don't want you to say, well, this can't be factored, because it clearly can be. I just want you to be aware that, again, the zeros are not real there. And so this makes a great problem for complete factorization in section 5. There's always a caveat here. There's always a, well, what if? Math problems, you know why I continue to take a problem and take it to the fullest extent is because that's what you have to start doing as future STEM professionals. Your boss is going to want you to think outside of the box and to come up with good ideas to help that business make more money or have a bigger impact. So just, you know, it's always good to look at things in a light that expands the understanding. Now, of course, if we want the y-intercept, we just want to say, okay, r of 0. Well, that's easy to do. If x is 0, these terms are 0, and we're just left with 6 divided by -3, which is -2. So we've done the hard part, and none of it was very difficult. I think by now you become professionals at this. Again, everybody, let me just make the comment here. Do not make careless mistakes with these problems. It's unfortunate that you do, because I think you have such great ability and you have such potential to do great work. Just remember, the asymptotes are lines. The horizontal asymptote is a horizontal line, so it must be y equal a number. The vertical asymptotes are vertical lines, so it must be x equal a number. And if there are no x-intercepts, then be happy with that, okay? Don't make up intercepts that aren't there. Sometimes I think you all just decide, well, the problem is trying to trick me and I'm just gonna put something down that makes no sense. No, go with what the problem is saying. But if you're doing a word problem, don't just stare at it. Try something that helps to move the process forward. Now, we can go ahead and do the plotting of all of these objects here, but let's just go ahead and do a little sign test. There's not much to check. What are the BVs? We only have 2. They're right here. So the BVs will be 3 and -1. There are no x-intercepts, so we've got what, -1, and we have a 3. Now, notice these are all degree 1 here. This part is always positive, so we don't care about it. So, of course, you can say, take a -10. You can do like a 0 and then a +10. So we can check one of these. The top is always positive. So we got plus. And then -10 here, that's negative. And -10 here, we get 2 negatives. So this is negative times a negative, which is positive. So this is above. And of course, I'm not going to draw through because these are vertical asymptotes, but we know it has to change because of the multiplicity and then up here. Now, if you don't like this, again, these multiplicities are odd, so it's going to have to change. But if you want to go ahead and check the signs, you can. I'm trying to utilize some of the theory that we've talked about to save you some time. But do not under any circumstances do this if you don't understand this process. You check the sign like I'm doing here for each one of these. Okay, I'm not going to tolerate you messing this up because you're saying, well, that's what you did in lecture. You do this because these are what? Odd multiplicity. That's the difference, ladies and gentlemen, between doing mathematics and making it up, okay? So be intelligent in your choices. Be good detectives. It's like you're solving a case. You're solving a problem. That's what we do every time we do mathematics. We're solving problems. We're doing a proof here, even though we don't write proof. We're doing a proof. We're validating all of the steps. Now, let's do our cheat graph. So we'll do the axes. Now, again, you know, the thing is, always practice doing this, even if you get to choose something in WebAssign. Ladies and gentlemen, if you really want to learn something, do the sketch. Do the sketch. When you're taking a test, you're trying to get finished quickly. I know that, but while you're doing your homework, do the extra work to get a better understanding. So when you do the quiz and the test, you do really great work. So now let's just look here. What do we have? We've got a 3 here. So let's kind of make the scale not too big so it doesn't blow up. And then we've got what? A 3 and a -1. So we'll spread this out a little bit. So let's see here. Say 1, 2, 3. And here we'll go like 1, 2, 3. And then we have a what? A -1 about right there. So go ahead and plot the, let's see, where are we? Y equal 3. So we got Y equal 3. And then let's go ahead and get the asymptotes. We have what? X equal -1 and X equal 3. So we'll go ahead and plot these. So we had X equals -1 and then X equals 3. Again, this process can be really quick depending on, you know, what you have to answer. We're kind of pulling out all the stops, so to speak. And now, let's see what we have here. We've got a y-intercept of -2. So let's see, 1, 2, so -2 about right here. And we have no x-intercept. So this is kind of one of those interesting things. Now here's this why I'm doing this problem. Notice for this part, we're going to go ahead and fill this part in. That's the easy part. We don't have much to do here. So I'll go ahead and extend this down a little bit. Between -1 and 3, ladies and gentlemen, let me get a little, there we go. When I wave my hands around in front, it redoes the focus. So I always want to go ahead and check that. Now, notice here, we're below, so we have to hug as we go from either side here. That'll be -infinity, positive infinity, -infinity, positive infinity. So in this case, we've got to hug this line here, pick up this point, and then go back down. So let's go ahead and draw that. So we're not really sure what the maximum will be. We'll just kind of guesstimate. We don't know. We're not going to plot 500 points. So the sign test will give us something like this. And in order to find that peak right there, that relative maximum, we'll need to utilize the calculus to uncover the horizontal tangent there. That's a horizontal tangent where we're going to have the relative maximum, because this function will have a derivative there. And so that's how that's the work you're going to do in calculus to determine what that actual point is. And again, we don't know. We just have a reasonable graph. Now, when you look over here, you've got the curve above the x-axis here. So it's above the x-axis, but notice here we've got to get up here somewhere. We've got to get up to this line and go infinity. So we're thinking, are we here and doing, or do we start here and then cross? We're not sure. That's when you have to think, okay, wait a minute. Is there a possibility that the graph actually crosses this horizontal asymptote? And the weird thing is that because of this quadratic nature upstairs and downstairs, sometimes that will occur. Now, if you didn't write it this way, it wouldn't be the end of the world. If you were picking some selections, you'd be like, well, okay, the only one that really makes sense is this one, and it does cross, but the others are crazy, so I'm going to go with this. So this is where we can say, is it true? That is, when we take the function 3x squared plus 6 divided by x squared minus 2x minus 3. Does this actually equal 3? Does it ever actually equal 3? Is the output ever 3? Well, you're thinking, if you look at this function here and you say, yes, yes, because here's the thing, the domain of this function is going to include every number except 3 and -1. And then you're thinking, if we did the last problem, we miss the horizontal asymptote because it's a one-to-one function. But now we kind of contradict that when we start getting these quadratic P's and Q's. The thing is that I think we're going to find that we actually do cross, whereas in the previous problem, we didn't. So we need to check this. Now this is extra. If you don't do this, it doesn't make the problem wrong. It's just, you need to think about it. So I move this around and I always mess up the focus. Okay, now let's check it. So let's do this equation. Let's cross multiply. So we have 3 times x squared minus 2x minus 3 equals 3x squared plus 6. Now again, this is extra, but it's important extra. So we have 3x squared minus 6x minus 9 equals 3x squared plus 6. Now notice, in our symbolic computation, the 3x squared is absorbed. Okay, and so now if we take, if you will, the -9, add that to both sides, that'll give us a 15. So we have a -6x. Now, of course, we can factor this, but let's just go ahead and write it this way. X equals, so we got 5 times 3, and we have -2 times 3. And so we get 3's absorbed, -5/2. Okay, well, there we go. So let's see, 2, 1, 2, 3. So right there is -5/2. And we cross the point, the 3 right there. So the idea here is that we hug this line and then we come down a little bit and then we pick up that point and then rise to infinity. So this is an anomaly that we didn't see in the previous problem. So notice here, right here, this gives us the point -5/2, 3. Right there. So you're thinking, wow, nothing is set in stone. And then you're thinking it's going to take some calculus to figure out here that if you have what appears to be a relative minimum, the calculus will uncover that. And that's what you're going to learn next term. And then, of course, this part's above the x-axis, and we don't cross the horizontal asymptote except at this point. So this will have to look like this. So this part's easy. This just all above the x-axis. We don't cross. We know we don't jump down and go back up because this is the only solution here when the actual graph crosses the horizontal asymptote. So we're assured that this has to be the case here. Again, positive infinity as we approach 3 from the right. So like I say, there's a lot of calculus here that we don't know. There are lots of intricacies here with the curve that the calculus would tell us. So don't worry that, if you're picking a selection in the WebAssign and you say, oh, my graph, this has got to be the graph. I didn't get that. But what it would be highlighting is that the graphs are generated with a computer. And so if they're plotting 1,000 points, you're going to see that point right there. And so the calculation would be what I've done here, where you say, is it possible for the range, in this case, to include 3, whereas in the previous problem, it didn't include the actual value given in the horizontal asymptote. So there are some oddities that can occur with these types of functions. And so don't never say never, as they say. Always keep the door open to some possibilities that may be a little bit different. So the rational functions, again, the basic idea, asymptotes, intercepts, quick sign test. And again, always check the factors. You know, if you've got some nice multiplicities where you can write this, be comfortable with it, fine. Otherwise, check the factors like I do here to make sure that you have that correct. Now, there was one other exercise that I want to share with you and just do a little recap here. It was another polynomial. I want you to look at this. Now I want you to write this problem down. This is from 3.7. So we basically finished the discussion on the rational, and I'm going back to 3.7 to say, okay, here's an example. And this example you could have done without chapter 3. And I want to show you why. Now, when we look at this particular problem, the first thing you notice when I've got here, solve the inequality, is you see basically that there is no 0 here. You've got a term here and you've got terms here, and you're thinking, well, you know, I really do need to get a 0, because if I'm going to solve this problem, I'll have to do a sign test relative to 0. Am I plus or minus? So the first thing we want to do, and I thought about this, do an uncover, just so you can kind of work this with me, since I don't, you know, have a whole lot of time left in the lecture. Now you're thinking, okay, well, we need the 0. So we say achieve 0 on right-hand side, just like we always do. So that means that we transpose these two terms, and then that says that x over 2 minus 6 divided by x plus 1 minus 5 must be greater than or equal to 0. Well, then you're thinking we need to do BV technique. So how do we do that? We do the common denominator. So the first thing that we notice when we look at this problem is we say, okay, well, what's the LCD? There's a 1 right there, so we need a 2. So this is symbolic computation, and we need an x plus 1. So now we do our LCD, and then we just configure these to be equivalent to the previous line. So here we have the 2, but we don't have the x plus 1. So we have x times x plus 1, just a little bit of algebra 2. And then, of course, here we have the x plus 1, and we don't have the 2, so we adjust the 6 minus 6 with the 2. And then, of course, the negative 5 here, we don't have the 2, so we hit the negative 5 with the 2 to get a negative 10. And, of course, we don't have the x plus 1, so everything's good to go. Now, at this point, again, just like we did before, we want to collect terms. So we've got x squared plus x. We have a negative 12, and we have a negative 10x minus 10 times 1, a negative 10. Now, this was a nice problem because, again, when you look at this, we have the x squared term, we have the x minus the 10x, which is the negative 9x, and then, of course, we have the negative 12 minus the 10, which is the negative 22. So you're thinking, well, the denominator is already set for BVs, and then, of course, when we think AC, so this will be a 1 times a negative 22, but we need the -9, so we focus on the -22. So we say a -11 times the 2. And of course, the sum here will give us the -9, and then the product will give us the -22. So that's an easy factorization. So now when we look at this, we think, okay, so with the AC method, we get x minus 11 times x plus 2 divided by 2 times x plus 1. Now, let's finish it. The BBs, as I've written here, will now be the 0 where it's undefined, -1, the zeros, 11, and -2. Now, like we've done before, I'm going to say a little bit about a hole in a function to finish up after we do this. These are all multiplicity 1. And so, again, at the -1, we don't really cross, so I'm just going to erase that so you don't think we're actually crossing this. We'll do like that. So we're doing a little gap here. So again, when you check here the -10, this will be a negative, -10, negative, -10, negative, 3 negatives, negative. And then of course, these are all multiplicity 1, so the sign's gonna change at all of these BBs. So we get negative, positive, negative, positive. Now, when we look back at the original equation, we want greater than or equal to 0. But we know at -1, that just makes it undefined, so that gets an X. But the -2 and the 11 actually get a check mark. So then we say, okay, where do we have 0 and or positive? So -2 to 1, not including the -1, -2 to -1, not including the -1, union, then we have 11 to infinity. So what I wanted to do was just basically remind you of the technique that we did before we learned chapter 3. So this didn't require any new techniques, but the chapter 3 techniques with the multiplicities we've done here. Now, I want you to think about a function with a hole in it and basically what it means. For instance, and you've done this before, this will just be the last thing. If we had a function t of x equals this, x minus 1 divided by x minus 1. You're going to say, well, that's the easiest function in the world. That just equals 1 when x doesn't equal 1. That's just a horizontal line. But notice, we just say, what's the domain? What's the domain of t? Well, it's all real numbers except 1. So basically, we say there is a hole at what? 1, 1. Because, again, the function equals 1 when x doesn't equal 1. It's just x minus 1 divided by x minus 1. So when we graph it, this is what I wanted to show you. At 1, 1, we just have a hole. So at 1, 1, there's a hole. Otherwise, we just have the function 1. So this is what we call a function with a hole. Again, we have a 0 in the denominator that's also a 0 in the numerator. So we don't get a vertical asymptote. The function doesn't become infinite. So if you see something like this in a problem, then you would not state x equal 1 as a vertical asymptote. So we'll say x equal 1 is not a vertical asymptote. Again, that does not, that violates the definition of BA. So be careful when you're doing these problems, or if you make up your own. These actually make fun problems because they make great limit problems in calculus, because functions with holes in them are still well behaved. When you look at this function is not becoming infinite. It's really very controlled. It just doesn't have 1 in the domain. So again, be sure that you always pay attention and that you address these definitions as standard as you work these problems, and don't make anything up. Just remember, when you do the inequalities, when you do the rational functions, it's all very standard, very straightforward recipe where you always think about what you're doing. So I think you're going to find that these problems are very interesting and kind of help you to consolidate all the different ideas that we've learned about. Now, where are we heading after this? Well, we're going to hit the exponential and the logarithmic functions. So again, we're still doing review of college algebra. So once we finish the logs and the exponents, we will move on to trigonometry. So that'll be the new part. So enjoy. If you have some time, go ahead and look forward or look into the, I'll post some problems on the next few sections. You might want to work ahead if you want, your choice. But enjoy finishing up these problems. I think you'll find that your work in college algebra and what we've done today will give you even more security. So thank you for your attendance today. Hallelujah, the rain has stopped. Professor Ron was tired of the rain. I should be grateful for it, but I'm glad that it has stopped. And you all have a great day. Thank you.
Have a good day, Professor Ron.
Have a good day.
You too. Bye, Kaylin. Bye, Jose. And you all, I'll send out invitations for office hours if you have anything left by then. Have a good one.
Thank you.
Bye.
All right, thank you, Professor.
Thank you.